Hello, this is Philip Myers of PEMY Consulting. Welcome to the second part of Unit 1 on engineering units for the plant and tank engineer. We're in the oil business and shipping is an important component of it. I want to take a moment to tell you about the largest ship ever built. It's a ULCC, that is Ultra Large Crude Carrier. The ship had a fully loaded deadweight of 657,000 tons and an amazing draft of 87 feet. It was too big to navigate through the English Channel, the Suez Canal, or the Panama Canal. She had various names including Happy Giant, Jauray Viking, Knock Nevis, Opama, and Mont. She was sunk during the Iran-Iraq War and finally scrapped in 2009. So I have a quiz for you. We have these different large objects and then this 3-inch diameter sinker used for fishing. Take your pick of the objects and figure out which one you could accelerate the fastest by pushing on it or putting a little small rocket engine on it. I hope you picked the sinker because all of these have the same weight in space, which is 0, but their masses are vastly different. These all have large masses, whereas a sinker has a very small mass. You can see that A is equal to F, the force, divided by the mass. So since the mass is very small, acceleration would be the largest for this sinker. In our thought contest of the previous slide, we learned that mass and weight are different things. Mass is an intrinsic property of an object, meaning how much matter exists in that object does not change anywhere in the universe. Weight, on the other hand, is the force created by the action of gravity on the object. In most cases, we are talking about Earth's gravitational field. In the SI system, the standard gravity is 9.8 meters per second squared. In the USCS, or US customary system, the standard gravity is 32.2 feet per second squared. You would never be confused about minutes or seconds with inches or feet. They are independent. The same is true for the pound mass and pound force. They are not the same thing, except for the name, unfortunately. You should never confuse the two. The clue is in the equation F equals ma. Force is made from mass combined with acceleration, so force and mass cannot be the same thing. One of the reasons for the confusion about weight, which is force, versus mass, comes from the weighing balance. A balance actually compares a standardized, calibrated mass with what you're trying to weigh. So when a kilogram of mass is referred to as weight, that's actually incorrect. But the kilogram of mass, if you get a balance point on the balance that you're weighing, that has the same mass as 1 kilogram of mass, and it's called 1 kilogram of force. In the SI system, the kilogram force unit is not used because it would cause the same confusion that we have with the USCS system by calling two different things by the same name. So in engineering work, do not use the kilogram force as it is a non-standard unit and is classified in the International System of Units as a unit that is not acceptable for use with SI. Instead, use the units, use the newtons. You will see the precise difference between weight, force, and mass as we go through the course. One precaution about units: sometimes you have the same unit combination for two different things. For example, torque or moment is force times distance. Its units are Newton meters or foot pounds of force. But work is also force times distance, Newton meters, foot pounds force. These are identical, but they are not the same thing. So a name the name joule for Newton meters has been given to the unit of work, so it should not be used for moment or torque, for example. Now this is our first detailed introduction to Newton's second law. This F equals ma has to be committed to memory. F is a vector, and so is acceleration, meaning that it has both direction and magnitude. Sometimes you'll see it written as the rate of change, d by dt, of mv, which is the momentum. This form is needed if you're going to deal with a comet where the mass is also changing with the velocity. But for typical engineering, we don't need to worry about this form. We also have another concept that's important: unbalanced forces, or net forces, you'll hear it called. It simply means you have a lot of forces acting on this little pebble here, and many of these forces cancel out because they're in opposite directions, or most of it cancels out. You're then left with a net force, a resultant force. So that's the meaning of F net or F unbalanced. Just to illustrate that, if I have a blue rectangular object sitting on a table, the force of gravity, mg, exactly cancels the force of contact from the table, sometimes called a normal force. So nothing happens, the object does not move even though gravity is acting on it. But if I push with some net force on the side, this object will accelerate according to F equals ma. Notice the units: 1 kilogram meter per second squared. This has to be memorized. It's mass times length times time squared. Because it's used so commonly, this unit is given, or group of units is given, the name the Newton in honor of Sir Isaac Newton. A word about engineering accuracy. This shows high accuracy but low precision. Low precision because the clustering is pretty loose. It's accurate because if you were to take the average of these points, it would be very close to the center of the bullseye. On the other hand, this has high precision but low accuracy because these points should be over here. Also, engineers often just report in their final work the number of digits that are way beyond what they know. That is not a good practice. You should really only report in the final work the number of digits that are significant, which is usually only a few digits beyond the decimal place. Because computers have the ability to run out 16, 18 digits, a lot of people just leave that in their final answers, and that is wrong because it implies an accuracy that you don't have. I'm going to illustrate that on the next slide. This is a plot of the gravitational field from the North Pole to the equator, or the North Pole to the equator and back to the North Pole. Gravity is about 0.5% less at the poles than at the equator. The reason is that if you're on the equator, centrifugal force is tending to throw you out. It's counteracting gravity. But also if you get on top of a mountain like Machu Picchu, you'll lose about 0.1% of your weight because you're further away from the center of the Earth. There's also variations that are caused by the position of the sun and moon, so accurate scales notice daily changes in weight. There are many other effects, one of them being buoyancy, and it's a small effect, but it does exist. So it would be ridiculous to point to report a weight to 15 decimal places when at best you're going to be in the order of 0.1%. So what have we learned in Unit 1? Improper use of units can hurt you. We've learned that you don't really need to rely on G sub C because it's fraught with the potential for error and it doesn't use your intuition. The pound is not a pound the world around. They're different things depending on whether it's mass or force. One thing that should be done by practicing engineers is to always subscript the pound with the symbol F for force or M for mass. Of course, it goes without saying that you have to know F equals ma, and we'll have examples coming up. Use only as many digits as you need in the final answers. It's fine to carry them through with the calculations to reduce round-off error, but when you report your final numbers, keep them limited to the significant digits. Thank you.